Hi everyone, this is section 1.4.1 from A Course in Mathematical Modeling by Mooney and Swift. This section focuses on closed form solutions. Recall that in section 1.1 we were introduced to a model for the Florida sandhill crane. This model was given to us as a recurrence relation, where x represented the number of cranes at time n. In general, the number of cranes in year n was given to us by the year of cranes in the number of cranes in the previous year, plus the net growth rate times the number of cranes in the previous year. We can generalize this as x of n equals x of n minus 1 plus r times x of n minus 1 if we're going to model some other population that's like the sandhill cranes, but that might have a different net growth rate. Notice that in this equation, we could actually factor an x of n minus 1 out of both terms on the right-hand side and rewrite it as x of n equals the quantity 1 plus r times x of n minus 1, where again, r is the net growth rate for the population. And if we do a simple substitution for 1 plus r, and now call it capital R, then we can write that even more simply as x of n is equal to capital of R times x of n minus 1. So thinking ahead, if we know what the population is at time 0, how do we compute the population at time 1, or the population at time 100? Well, let's actually start with some simple examples that are a little bit more straightforward than the sandhill crane. So let's suppose that we know that the population at time 0 is 100. And this time we're going to use a net growth rate of just 0.05. And so this makes capital R, 1 plus that little r, 1.05. So to compute x of 1, the model equation tells us that we'll take 1.05, that capital R, times x of 0. And we know what x of 0 is. So we plug in 100, multiply it by that capital R, and we get 105. That's not too bad. Now let's continue with the same initial condition and the same capital R and look at computing x of 100. Well, our model equation tells us that'll be capital R, 1.05, times x of 99. Okay, well, we don't have x of 99 right now, but I could just use the model to compute x of 99. And the model tells me that's 1.05 times x of 98. Okay, don't have x of 98 either. I could compute x of 98 using the model, but I think you all already see the problem, is that to compute x of 100, I need to compute all values of x from 0, starting at 1, up to 100. Now we could do that if we had plenty of time, just with pencil and paper. Next week, we'll see how we might do this more quickly using technology like a spreadsheet program. But for the time being, let's see if we can come up with something a little bit more clever when we're stuck without a computer. So what we're trying to find is what's called a closed form solution. And a closed form solution to a recurrence relation x of n is a function only of n and not of the prior values of x. So the idea is if x of n is a function only of n, then when I want to compute x of 100, well, that would be as simple as plugging 100 into that function. And right away, I have my result. So that's easier, it's quicker just overall better. So here's a question. Can we find such a solution for the sandhill crane model or a model for a similar population? Well, let's see what that would look like. So just for fun, let's think about computing x of 1 again. So now this assumes that we have x of 0, and usually we do know what our initial population is. So our model tells us x of 1 is equal to capital R times x of 0, which we've already seen. Okay, well, what about x of 2? Well, the model tells me that's R times x of 1. And as it turns out, I computed x of 1 above, right? So I can actually plug in the right-hand side of this top equation in for x of 1. When I do that, I have R times x of 0. Again, just swapping in the equation in this upper right-hand side of x of 1 for the term here. Simplifying that, I get r squared times x of 0. So now I've related x of 2 in terms of x of 0, and I've cut out the middleman x of 1. If we continue this approach and look at x of 3, well, my model equation tells me that's capital R times x of 2. And just as before, I've computed x of 2 in the step above. So now I can substitute this expression in for x of 2 and use all of that hard work that I just completed. So that'll give me capital R times r squared, x of 0, and simplifying, I get r cubed times x of 0. So now I've related x of 3 all the way back to x of 0, and I've cut out two middlemen, x of 1 and x of 2. So really what I've got so far is that x of 1 is capital R times x of 0. X of 2 is r squared times x of 0. X of 3 is r cubed times x of 0. And you might be starting to see a pattern that we can use to our benefit. So in general, what we have is that x of n is capital R to the n times x of 0. And intuitively, this makes sense to us because at every time step, we've multiplied our initial population by another instance of capital R. So after n time steps, we have n factors of capital R applied to x of 0. So a couple of quick notes. The first one, primarily for fun, is to let you know that the method that we just applied to come up with this closed form solution is called the iterative method, because we came up with the solution by iterating x1, x2, x3, etc., until we found a pattern. The second note is that this closed form solution is really important. It's so important that it has a special name and a special proposition associated with it. No surprises here. We call this the exponential growth model. Notice that it looks a lot like exponential models you've seen in the past. Now, a lot of times when I introduce this to students in courses other than Math 470, I might show this equation as y equals ab to the x, or maybe q equals ab to the t. But in either case, I've got some quantity that I'm interested on the left-hand side. And on the right, I've got my initial value, which in the blue text is represented by the letter A. And then I have some factor that's applied to a variable number of times. And in this case, the factor is b, and it's applied either x times or t times, etc. So that aligns with the equation that we have, where the quantity that we are interested in on the left, the population size at time n, is equal to the initial population x of 0, so that's acting like our little a, and then a factor, capital R, that's applied to x of 0 n times. Now, proposition 1.1 from our textbook tells us the behavior of this exponential growth model over time based on the value of that factor, capital R. So the population will grow exponentially if capital R is greater than 1. It will decay exponentially if R is between 0 and 1. It will be a damped oscillation if R is between -1 and 0. It will be an undamped oscillation if R is less than -1, and it will be constant if that factor is exactly equal to 1. Here's a question for thought. What will happen if that factor is equal to 0? Well, just plug in capital R equals 0, and you see that for all time, the population level is 0. So we never actually have a population, or if we do, it immediately goes extinct. So while that could be a very sad case, mathematically, it's not terribly interesting. Our next example is what's called the affine recurrence relation. It has the base of the exponential recurrence relation model, x of n equals capital R times x of n minus 1. But we add a constant term of a into our model. Examples of quantities that follow this type of model might be something like a savings account that earns a certain percentage interest over time, but that you also contribute to at regular intervals the same deposit amount, right? So the amount in your savings account at time n would be the amount you had before, incremented by the interest rate. And then you would add your deposit amount to it. So here's a challenge for you before next class. See if you can find a closed form solution for this affine model using the iterative method that we used to find the closed form solution for the exponential model. I'm excited to see what you come up with. Good luck, and thank you for watching.